example model in AnyLogic, okay? So specifically, it will be this model called the game of life, okay? And what I'm going to do here is go load this myself, okay? So let me just close this up, and I will follow you. Okay, so here, help, example models, and I believe it's just down in this list here. Sorry, under T? Okay. Now why isn't this? I think. Okay, it's a strange thing. Sometimes it shows all of them, and sometimes not. Okay. Come on. Okay. So miscellaneous. It may be something to do with screen size, or what have you. Give me a minute here. It's an odd thing. I'm wondering if it's over on the right-hand side or what. What's that? It's under miscellaneous? Okay, thank you. Thank you. Yeah, quite right. Okay, so the game of life. Thank you. There we are. Okay, good. Okay. So, here we go. So you'll see that the game of life has three major components to define it, to specify it. So some specification is associated with the cells, which are going to be, each of which is going to be uniquely mapped to a particular grid location in that 100 by 100 grid. Main is going to specify that grid as well as other characteristics, and then we have a simulation to run it. So let's go take a look at how this model works. First, just to engage people, let's run it first, okay? So I'm going to right-click on this. I didn't plan this, but I think it's worth sort of getting a glimpse of its dynamic behavior. So let's run this thing, and what we see is a set of cells displayed in a grid. I believe this is indeed a 100 by 100 grid, and those cells are exhibiting some behavior over time. The behavior that they're exhibiting is based on purely local rules that update the state of a given cell every time step, discrete time step. It updates it based upon a deterministic function of the cells to its north, south, east, and west. 4 sides, okay? And what you'll see is there's some rather articulated behaviors here. For example, there's some sort of things going on over here that they're exhibiting continual interaction. And you might notice, depending on the vagaries of the random number seed, etc., there are sometimes objects that sort of glide across the screen, and other objects that are larger scale structures that evolve in kind of an oscillatory way. And you already see some oscillations here, these little items here. And in fact, in the early days of computers here on the MIT campus, well, it wasn't early days of computers, early days of mini computers, in the 70s particularly, there was a massive amount of computing power that went into simulating this game. And it was predominantly for amusement of the research students, the research scientists and graduate students involved. But there was some seriousness of intent with respect to it. In fact, these various things that are on the screen have various names that were given to them in the 70s. And people figured out that this game actually had significant conceptual implications because it was so-called computationally universal. Out of those rules that lie behind this game, which we'll see are very, very simple, you could actually build a computer. And that computer could then be used to simulate anything a normal computer can do. It's computationally universal. It's a language that can be used to solve arbitrary computer problems. And it's described with just a few basic rules. Let's talk about this setup. Okay, so this was first articulated by a mathematician named John Conway, who was an English mathematician, who was modifying some ideas by known as someone named John von Neumann, who was really one of the key founders of computing, the modern types of computing, and has the classic computer architecture used to this day, the von Neumann architecture named after him. John von Neumann was interested in sort of theoretical models of computation. How do you describe in a theoretic way what a computer does? Putting aside the issue of whether it's a silicon or gallium arsenide or light-based computer, there's something about computation that transcends the materials that define it. There's something about computation that can be used, can be played out in any number of different structures or materials. And he was interested in describing it. And he made use of what are known as cellular automata, which are basically a mode of description of computation which divides up space into cells and has time jump forward in steps. Okay? And there are rules that govern how the cells in the next time step depend on the cells in the previous time step. So it evolves, and in many cases in a deterministic way. So this game of life reflects this. Von Neumann had a very complex model of computation, and Conway came up with this much simpler model that still captures this computational universality property. The fact that you can take your most powerful computer in the world, you know, the Chinese supercomputer that's the current world leader in terms of computational power, and anything that computer can do can be simulated in the game of life. It just will be slower. Okay, so Conway came up with this very simple but compelling game, and it was inspired in many ways by the life course of cells. So the idea here is that a space, one of these grid cells, either contains a living element or not. It either has a living cell or there's nothing there. You call it dead, okay, for now. And then there's stylized rules for when a cell gets born and when it dies, okay? These are all deterministic rules. And what you see is that while many things evolve in a way that leads to sort of very simple residues, there are some things that are extremely complex that can come from it. Let's talk a little bit more about this. First of all, I want to emphasize up front, there's no mobility in this model. Okay? There's no, although you may see moving patterns on the screen here, and you may see what seem to be shapes evolving in sort of some sort of fixed way, like say so-called stoplights. You'll sometimes see these structures almost moving in a predefined way across the space in sort of some periodic fashion. No one cell is moving. A given cell is either alive or dead. Okay? There's no hopping to another place. So it is a situation where there's no mobility applying. Cells are viewed as surrounded by four neighbors exactly, north, south, east, west. That's it. They're not connected logically to their neighbors in the diagonal direction, only to the direct neighbors. Now, using the analogy with cells, what Conway posited for the sake of this game was sort of a stylized representation where cells need a certain amount of space to live, a certain amount of free space around them. They can't be cut off from blood flow or what have you by other cells entirely. But they need some other cells nearby them to continue to live as well. So they require some neighboring empty space, but also some proximity to nearby cells. Okay? There needs to be enough of a neighborhood around them of other cells that they don't die from isolation, but not so many that they die from crowding. Okay? And an empty cell becomes occupied here if it has an ideal nurturing environment, if it has three cells around it to which it's connected. So if there's an empty cell which is surrounded by 3 cells that are occupied, that cell itself becomes, it gets born, so to speak. A living cell is established there. The colonization occurs within. And an existing cell dies if it's too isolated, too few neighbors, too crowded. It's surrounded by too many other cells. It has 4 surrounding cells. Okay? So these are the basic rules of the game of life. And you can actually specify them much more succinctly. Okay, so let's open the main class. Okay? So double click on